This next chapter, there's a lot of topics. We want to figure out how properties can be related, because some properties are easy. They're easy to what measure? Temperature, do you think that's easy or hard to measure? Let's put it in the easy category. How about pressure? Pressure, easy or hard to measure? Easy. How about mass? Easy or hard to measure? Easy. Hey, there's all these easy properties. We're getting to some hard. Just give me a minute. How about density or specific volume? Density or the inverse, 1 over specific volume. Easy or hard? It's pretty easy, actually. But let's do internal energy. You tell me how you're going to measure internal energy. Hey, it's a property. We've been talking about it for the last 2 semesters. I think we're going to put finally somebody in the hard category. But you know, we never really talk about internal energy as a value by itself. It's always with respect to a reference state. We often forget about that reference state, but it's embedded in the tables and you can often find it and remind yourself. So it's really the change in internal energy. Mass truly is measured from no mass up. There's not like negative mass. But you can have negative internal energy because maybe the condition of the state is colder than the reference. So we talk about changes in U. How about enthalpy? You want to put it in the easy or the hard category? It's really in the hard category. I say, go get me an enthalpy meter. You know, you can get a pressure gauge, get me an enthalpy gauge. You can get a temperature measurement, you know. How are you going to get an enthalpy measurement? Hard. And we're really interested in how changes in H. It's just the same discussion. And then entropy, easy or hard? Can you go down to Walmart, buy something to measure entropy? You could go to Walmart and buy something to measure temperature and maybe even pressure. They may have pressure gauges there. So this really, I hope, gives you a roadmap. It's how do I measure these hard properties? And guess how you measure them? You measure other things and then infer those values. And if you really go back and you think about how did you actually measure temperature, guess what a thermometer does? How does a thermometer work? It's the height of mercury in a thin little column. And when it's higher, the mercury goes higher, higher temperature. And then it's colder, it's lower. You're just doing a visual measurement of length and inferring temperature. And you're exploited a property about how the density of mercury is sensitive to temperature. Or thermocouple. How many people take M&I in other classes? You've seen a thermocouple? How does that work? You measure something and infer temperature. You measure little millivolts because dissimilar metals put together, 2 types of wires put together on one end, on the other end, they connect, they make a loop. And if their junctions are at different temperatures, you have a little millivolt type of potential that would drive current. So that's how thermocouples work. So often, we don't measure temperature directly, we measure it indirectly through some relationship. It's the same game when we talk about how to measure entropy, enthalpy, and internal energy, although they're a little more abstract to us. But you're going to measure probably something like pressure and temperature and volume and infer changes in internal energy, changes in enthalpy, and changes in entropy. This is a long chapter. The backbone is mathematical relationships. Then we get some property relations, how to get changes in entropy, internal energy, enthalpy. And then we talk about other properties, volume expansivity, isothermal compressibility, isentropic compressibility, the Joule-Thomson coefficient, and then how do we construct those tables and put them in appendices so you can use them, or put them in a computer program so you can use them. We're not going to cover the enthalpy and entropy departure charts. So equations of state. The easiest equation of state is this one, PV is equal to RT. It just relates temperature, volume, and pressure. Sometimes you'll see it like this. What did we just change? Instead of being on a mass basis, it's on a molar basis. What are the units of this entity right there? It's specific volume, but instead of meters cubed volume per kilogram, it's meters cubed per kilomole. That's right. And instead of being the gas constant, it's the universal gas constant, having units of 8.314 kilopascal meter cubed per kilomole Kelvin. That's the universal gas constant. Here's another equation of state, an EOS. Sometimes you'll see that EOS. Van der Waals equation. Well, we understand R bar and V bar. There's a V bar squared. What do they have? They have constants that help fit. So the value of A and B depend on this fluid or this substance. Redlich-Kwong equation of state. Another constant. It's not the same A and it's not the same B, but they're different curve-fitting parameters to make that equation of state fit the data. There's temperature to the half and V bars. The Beatty-Bridgman equation. You can see how V bar is here, etc. V bar squared. The beta, gamma, delta, curve fit parameters. What is the title of this chapter? Thermodynamic relations. What's the point? Some properties to other properties, especially those that are hard conceptually for you to figure out how to measure. You can measure some, infer the value of others. Mathematical relations. What's the similarity between the title of this section of that chapter and the whole chapter? Thermodynamic relations, mathematical relations. Mathematical relations are the backbone on which we derive those expressions, those relationships. So what is this? Does this equation look similar to you? It says if I have a function z, if it's a function of x and y, then I know that a small change in z can be expressed as a small change in x and a small change in y through this relationship. Does that equation look good? Do you remember something like that? It's multivariate calculus. What about this relationship? It's called the reciprocity relationship. How does x change with respect to y holding z constant? Multiply that by how y changes with respect to x holding z constant, and it'll always be equal to 1. This is the cyclic relationship. This one throws students for a loop because they think, that shouldn't be a minus sign. Because they just saw this one, they say, oh yeah, cancel the dx's, cancel the dy's. Of course, it's 1. But look at this one. Change in y with respect to z holding x constant, change in z with respect to x holding y constant, change in x with respect to y holding z constant. Let's just cancel the changes in y's. Let's cancel the changes in z, that cancel the changes in x. Why is there a negative sign? Well, there is. There is. It's math. All right? So that's a cyclic relationship. We use these as building block tools to develop our mathematical relationships. We go back and we recall two relationships. The first and the second TDS relationship. This is one of the major building blocks. And then we use those mathematical relationships to build others. We use these to develop way back when how to get an expression for entropy changes, especially for ideal gases and incompressible substances. That's what we used them for back at chapter 6. Now we're going to do it for anything. It doesn't have to be an ideal gas. And it doesn't have to be an incompressible substance. What is the change in S for an incompressible substance? Is it C natural log of T2 over T1? Does that equation look familiar? Yeah, right? Which one of these did we use to go there? The first or the second one? How about the first one? If it's incompressible, which term, this term, or this term is 0 for incompressible? The last one. Why? Incompressible, no matter what the other properties are doing, what is the specific volume? It's not changing. So change in the specific volume, 0 for an incompressible substance. No matter if T changes, or P changes, or U changes, or S changes, delta, or the change in V is 0. So look at this. We have du is equal to T ds. True? Put the T over here. Maybe I should put it like this. ds is equal. For an incompressible substance, is du equal to c dt? Yeah? And now we say, hey, you know what? We can do this integrate and integrate. The constant typically comes outside. Not the constant. We treat the specific heat as constant specific heats. Otherwise, you have to leave it inside. And you get that from S1 to S2, that's the change in S. That's S2 minus S1 is equal to C times integrate from T1 to T2, the natural log of T2 over T1. So what do? You develop some additional property relationships. Let's take a look at the roadmap here. Start with the first TdS equation. Great. Recall that think about Z as a function of x and y, and in general, dz is equal to dx. Just this relationship right here. The change in Z can be related to a change in x and a change in y. Well, for this equation, let U be Z. Move from the general to the specific. Let S be x and let V be y. And so what we find is that because U can be expressed as a function of S and V, you find that du is equal to the rate of change of Z, what was Z again? U, the rate of change of U with respect to x is S, holding y constant V times ds is equal plus the rate of change of U with respect to V holding S constant times dV. You see that? We just took the general mathematical relationship and applied it, knowing that from the state principle, U can be expressed in principle as a function of S and V. Now you look at this, and you look at this, and you just compare apples and apples and oranges, right? So let's rewrite this. du is equal to T ds minus P dV. If that's true, I have a 1 in front of the du's. I have a ds. Guess what is equal? The first relationship. Temperature is always equal to the rate of change of internal energy with respect to entropy holding specific volume constant. True for an ideal gas, true for a real gas, true for a two-phase substance, true for a liquid, true. Got it? Likewise, negative P is equal to du dV holding S constant. Negative P is equal. That's how you get these relationships. So you're building relationships between properties and changes in properties. There's two additional properties. One called the Gibbs function, lowercase g or cap g. If it's lowercase, it's per unit mass, right? And then the Helmholtz function, lowercase, whatever that is, psi. Or that's not a lowercase, it's just psi. You can read more about the meaning of the Gibbs function or Gibbs free energy. This textbook sort of they just drop in off of the planet Mars. Here it is. What's it used for? Don't ask. Comes later. Not in this chapter. Just here it is. It's a new property. It's helpful. Same with the Helmholtz. But what does this property look like? If I had H plus T naught S, what would you say to that? What does that look like? What does that property look like? Exergy, right? Right? Is that exergy? All right. Anyway, so there's a couple different names out there used in the vernacular. The recommended name is Gibbs energy or Gibbs function. It's a thermodynamic potential that measures the usefulness of process initiating work obtainable from a thermodynamic system at a constant temperature and pressure. So it's isothermal and isobaric. All right. Helmholtz function, Helmholtz free energy, potential that measures the useful work obtainable from a closed thermodynamic system at a constant temperature. It's a combination of first law and second law. Just like we had, what other property was a combination? Exergy. First chapter we started with in this textbook for this semester, right? Exergy, true? It had some, exergy was some maximum useful work obtainable. Here's the interpretation in the context of a closed system. But you can, it's like enthalpy, remember, right? H is equal to U plus PV. Talked about flow work, but then we used it anywhere. We could use it anywhere. We can get the classic Maxwell relations. If you take thermodynamics, there's a few things you should hear about. One is, oh, the Maxwell relations. Well, there they are. They're just relationships between properties. Here, they look pretty abstract, don't they? Here's one of them. So how does temperature change with respect to specific volume holding entropy constant? It's related to how pressure changes with respect to entropy holding volume constant. I don't know. They're pretty abstract, cold and hard, right? So the Clapeyron equation, let's just look at it. Here it is. It's the how does the pressure change with respect to temperature along the saturation curve. In your mind, put out a PT diagram. This is one of the most important plots in all thermodynamics. You saw it in chapter 3 in Thermo 1. You were so impressed with it, you memorized it. You have a visual image in your brain. You could write it down now from memory. You could write it down 5 years from now from memory. And you could write it at the end of your engineering career from memory because it's so important. True? What's this plot look like? This goes on and on. This goes on and on. This terminates. What's this point up here that terminates? The CP. What's this one? The TP. Got it? Right? So basically what they have is they have a plot of pressure versus temperature, and you have the derivative, the slope of that plot, and it can be anywhere along this line right in here, especially when we're going from liquid to vapor. But you know, we're only going to do it for this one right here because it's the Clapeyron equation. Look at this. What's H of G? What's H of F? The enthalpy of saturated, H of G is saturated vapor. H of F, saturated liquid. It's how do you get the change in enthalpy, the heat of vaporization. This right here is HFG. All right, what's T? If you've been shy, you're kind of, you know, not sure of answering some of these questions, here's your chance. What's T? Temperature. Congratulations. And now what's V sub G and V sub F? The volume. So if I have 1 kilogram at that pressure, that temperature of saturated vapor, what volume does it occupy? And if I have 1 kilogram at the same temperature and pressure of saturated liquid, what volume does it occupy? V sub G and V sub F. So this equation, we want to drive it. Okay, well, how are we going to drive it? Start here. That seems like a weird place to start. I know other people smarter than you, smarter than I, figured this out a long time ago. A guy named Maxwell, right, and Gibbs, over 100 years ago. They said, start here. I don't know why, but let's start there. What do? You say the change in pressure with respect to temperature holding V constant is equal to the change in entropy with respect to specific volume holding T constant. True? We want to apply it for a phase change region, going from saturated liquid to saturated vapor. Okay? So this is just, I can rewrite like that. Why can you just rewrite that? Because it's pressure and temperature not independent in that phase change region. There's only one saturation pressure for each temperature. So this partial derivative becomes an ordinary derivative. All right? And it's applicable, we remind ourselves by saying, hey, this is only along that saturation line on our PT diagram. How about over here? Well, this is, we're going to go from saturated liquid to saturated vapor. So S of G minus S of F, how much that changes with respect to V sub G minus V sub F, how much the volume changes at constant temperature, at that temperature in which it's changing. That's how far you take this first equation. Now you jump over to this equation, TdS relationship. What? Yeah, this is we want to use both of these and combine them to get the Clapeyron equation. So what do we do here? Well, so we have T times S of G minus S of F equal to H of G minus H of F minus VdP. But what about this VdP? If I'm undergoing a phase change at constant temperature, tell me about the change in pressure. There's no change in pressure, right? You can boil or condense at constant pressure. So this whole term is 0. So now what I do is I say I'm going to use this relationship to get S of G minus S of F is H of G minus H of F divided by T. I'll substitute that into this right there. And our final relationship is what I wanted to show, the Clapeyron equation, how the change in the saturation pressure with respect to temperature is equal to H of G minus H of F divided by T times V sub G minus V sub F. It looks pretty abstract, but look at which parts of these are easy for you to conceptually think about going out and measuring. Would this group of terms be easy or hard to measure in the lab? Pretty easy. How about this group of terms? Easy or hard to measure in the lab? Easy. This temperature, easy. This gives me a way to get HFG, the heat of vaporization, from easier measurements. That's the beauty of it, okay? How about derive the Clausius-Clapeyron equation? Well, this is the Clausius-Clapeyron equation. Where are we going to start? Let's start with the Clapeyron equation. Okay? So if you start with the Clapeyron equation and you make some assumptions, I'm going to assume that it's V sub G is much, much greater than V sub F. Think about that. Remember in our steam tables, water changing phase? The V sub F was typically very, very small. And V sub G was much larger than V sub F. So if you take a look at this equation, just neglect the small term. The second one is that the vapor behaves as an ideal gas. What do you mean by that? That means that P times V sub G is equal to RT. Notice they have an R right there. Isn't that the same R as right there? Isn't that our gas constant? Was there an R in the Clapeyron equation to begin with? I need an R. You're going to get the R from the ideal gas equation. So what you do is you have P is times V sub G is equal to RT. Okay? So I can replace this right here. I can replace this V sub G. All right. Also, this delta H, what is that? Is that simply H of G minus H of F? Is delta H, is that what that's equal to? That is. Okay? So what do is we start to make it look like the Clausius-Clapeyron equation. We have delta H just by name calling. T, we have V sub G, which is R, T, P. Make sense? So what's the next step? Take a look at where I want to go. I want to go over here. I got the RT squared delta H, but I don't need this P. What should I do with this P? Put it over here. True? Does that make sense? Now, everything on the right-hand side looks good. What about the left-hand side? I have to recall things from calculus, which I don't like to do, right? And so I recall something like this. the derivative of the natural log of x with respect to x. Do you remember how to do that derivative? 1 over x. Perfect. The derivative of the natural log of y of x with respect to x. How about 1 over y dy dx? So what we do is we look at this and we say, this is 1 over y dy dx. That's nothing but the derivative of the natural log of y with respect to x. Oh, I know. That was obvious to you before I started. No, it wasn't. It's like, deep in our recesses, there's some mathematical manipulation or trick or some relationship that you needed to pull out. But there is our RT squared. There it is, QED. That is our Clausius-Clapeyron equation. In the single phase region, you get an equation like this. The change in enthalpy can be related to an integration of C sub P with respect to temperature, and then the integration of something complex, look inside the integrand, V minus T dV dt, holding P constant with respect to P. How in the world can we derive this equation? Well, I used to spend more time doing this, the derivations in the textbook. And it starts like, oh, well, I'll start here, and then I'll use these Maxwell relationships. Then I'll start here, and then I'll combine and recall, put it together, and voila. More important is how do you use a relationship like that? So let's go back to this relationship right there. And I say, now, for an ideal gas, this doesn't have to be restricted to an ideal gas, but it applies to an ideal gas. Assuming constant specific heats, what does this relationship do? And so the change in enthalpy is equal to what happens right here if it's constant specific heats? Comes outside. Then you have the integration with respect to temperature. That's just the change in temperature. That's just C sub P T2 minus T1. How about this term? V right here is equal to RT over P for an ideal gas. The change in V with respect to temperature, holding pressure constant, is R over P. You multiply that by T, you look at it, it goes to 0. That whole second term is 0. And so for ideal gas, constant specific heats, the change in enthalpy is simply C sub P delta T. There's another property, volume expansivity. This is typically the definition given, and then you can show that it follows that this is also true. How do you do it? You just recall V is equal to 1 over rho, and you are honest with the mathematics and the differentiation and the calculus, and you get the same relationship. It looks different, doesn't it? It looks like that minus sign's out of place, but you need that minus sign. Okay. Now for the volume expansivity, that's this term, beta, 1 over V dV dt holding P constant. Evaluate it for an ideal gas. Well, for an ideal gas, we know that PV is equal to RT. And so V is equal to RT over P. So this beta is equal to 1 over V, derivative of V with respect to T holding pressure constant. We can substitute for this V right now. So that's RT over P. And now we just have to do the derivative. The derivative of V with respect to temperature holding pressure constant is R over P. Substitute R over P. P's cancel, R's cancel. And you get the relationship that for an ideal gas, beta is 1 over the absolute temperature. When I teach heat transfer, I'll say 5 times. The temperature must be absolute temperature. And then I give them a problem. I say calculate beta when the air temperature is 20 degrees C. And you know how many students on the final exam in heat transfer put 1 over 20 degrees C? So I tell you in heat transfer, beware of that trap. I tell you in thermodynamics, don't do this mistake, right? So there you go. This has to be absolute temperature. Now also, when I teach heat transfer, some people will say, oh, I have liquid water. And liquid water can be hot and cold, and you can get natural convection of liquid water. But I need beta for liquid water. I'll use 1 over T. They forget that this started with ideal gas assumption. This only applies to ideal gas. Now, if you get a different equation of state, you can get a different expression for beta. What about beta for liquid water then? You have to go find it. It'll be listed in a table. Typically, there's not a simple analytic expression for it. What are we showing? This is the density of water. It's 100 kilopascal, 1 atmosphere. The temperature ranges from 0 to 10 degrees C. It's in the liquid state, right? All right. Take a look at the values. It's around 1,000 kilograms per meter cubed. But you can see that it reaches a maximum at around what temperature? 4 degrees C. And so what happens if you cool liquid water below 4 degrees C? Let's say you cool it to 2 degrees C. Does it expand or contract, liquid water? Yeah, it expands. It's the most dense at 4 degrees C. It's the highest density at 4 degrees C. Maybe I should have plotted the specific volume as a function of temperature, and then it does this. So that at 4C, it's the lowest volume, and if you get it colder, it expands. You get it warmer, it expands. All right. So think about this. What is beta, the volume expansivity, of liquid water at 4 degrees C? Right there. Well, you can say, what was the definition of beta? 1 over V, dV, d, T holding P constant. P is constant. So what about this? What is beta at 4 degrees C for liquid water? Help me now. Come on. The derivative is 0. Multiply anything times 0. What do I get? 0. Beta is 0. How about if I do it at 2 degrees C? You get the negative 1 over rho, change in rho with respect to T holding pressure constant. What is this derivative at negative 2, or at 2 degrees C? It's positive, true. Then you have 1 over rho, then you have a negative sign. So beta is negative. It's negative over here. What about at 6 degrees, 8 degrees, 10 degrees C? The slope is negative. This 1 over rho is about 1 over 1,000. And then you have a negative, it's a positive. So beta is positive out in this region. So beta changes at 4 degrees C. I'm going to go ahead and stop.